Corrosion is a breakdown of essential properties in a material due to chemical reactions with its surroundings. It's really oxidation that causes the loss of electrons in metals which react with water and oxygen, creating deterioration. In iron or steel, this is also called rust. Using corrosion prevention, control, and mitigation techniques, we can slow the corrosion process of metallic materials, degrading back to their natural state. So, how do we slow this natural process? We shield, we insulate, and we attempt to protect the surface from the environment so that it doesn't complete the corrosion cell. One important way we do this is through the use of polymers. Hi, I'm LeVar Burton, and I'm going to be your guide through the remarkable world of polymers. Natural polymers have been around for thousands of years. Starch, cellulose, lignin, and rubber are polymers that naturally occur in plants. Proteins, nucleic acids, chitin, and glycogen are natural polymers which occur in the animal kingdom. On the other hand, synthetic polymers came into prominence around the time of World War II. Till then, the concept of macromolecular chemistry was familiar only to a small group of chemists, and only a few polymers were sold commercially, such as vulcanized rubber, artificial silk, bakelite, and solvent-resistant rubber. Starting with the invention of polyethylene in the early 1930s, polymer science progressed by leaps and bounds with the invention of food-grade plastics such as polyester fibers, polyurethanes, polycarbonates, and hydrogels. These inventions laid the groundwork for polymers in the 21st century. But what exactly is a polymer? The etymology for the word polymer shows that it is derived from the Greek words poly, meaning many, and meros, meaning parts. So we can deduce that the easy definition of a polymer is made from many parts. Those parts are called monomers. More scientifically, though, a polymer is developed by linking together small molecules through covalent bonds. Now, a coating is defined as the layer of a substance spread over a surface for protection or decoration. Coatings are usually in liquid or liquefiable form to spread out over a surface. So what is the molecular makeup of a polymeric coating? You take a polymeric binder and solid particles, and when they bind together, they form into a composite, and a polymeric coating is born. In our quest for a coating that can defend against the environment and decelerate or passivate the corrosion cell, what are some of the attributes that we strive for? Well, things such as electric insulation, aesthetics, wear and tear, inhibiting the diffusion of gases including oxygen, the repelling of water, chemical resistance, and of course, anti-corrosion properties. These are all necessary characteristics or byproducts for a superb coating. Polymers, and more specifically, polymeric coatings, have helped mankind and will continue to do so. However, there is no such thing as a perfect substance, as everything has both positive and negative attributes. Polymers themselves may eventually degrade. Mechanical properties of composite materials over time will deteriorate under hot, wet conditions. Likewise, polymeric coatings and materials may chemically degrade with exposure to ultraviolet light. Some polymeric materials may be degraded by certain chemicals or dissolved by organic solvents. Often, polymeric materials are formulated to include other chemicals to enhance a specific required performance. One of the inherent risks of using these enhanced materials is that the incorporated substances eventually degrade, releasing chemicals that can be a long-term environmental risk if not properly managed. Still, I want to reiterate that polymers have wonderful properties as well, but you don't have to take my word for it. We've interviewed Professor Shelby Thames from the University of Southern Mississippi, who will talk a little bit about synthetic polymers and polymeric coatings.
Polymers are of generally two types, natural polymers and synthetic polymers. Natural polymers are examples of those are wool, silk, and synthetic polymers are polymers that are man-made, that are made in our laboratories and transferred from our laboratories into manufacturing facilities and then into use. The first synthetic polymers were developed in the 1900s, and they were phenolic resins. And then after that became oil-modified polyesters. And then following on the heels of that were nitrocellulose lacquers. And we probably all heard of those because they're widely used in the furniture industry. And then in the mid-1900s, we had a class of polymers called thermosetting polymers. They were thermosetting acrylics, meaning that we have to apply heat to make them transform themselves from a liquid to a solid polymer. And after that became a class of polymers called urethanes. Urethanes are extremely tough and durable, and they're an excellent class of polymers for a number of different kind of applications: coatings, adhesives, elastomers. And then we had in the same time frame melamine formaldehyde polymers. All of these polymers that I've talked about are in use today and continue to be used. The World War II era initiated a non-rubber latex development with the introduction of styrene butadiene. For instance, the warfighter needed tires and tank pads made out of natural rubber, and they used all the natural rubber sources that were available to us, and we had to turn them into synthetic polymers, and that's where the styrene butadiene latexes came from, out of a need for a war. Significant corrosion protection came from the work of George E.F. Brewer. Dr. Brewer issued in what we refer to as the electrodeposition of coatings. He utilized the anodic deposition polymers for his work, and later it was found that when you use cathodic polymers who were deposited on the cathodes, you got better corrosion protection. And today, the automobiles that we use today, that we drive today, the trucks, the cars, and so forth, their frames are protected from corrosion by cathodic deposition of polymers. My colleagues and I use polymeric materials every day. We use them to meet the needs of society, to minimize material degradation, to provide greater predictability of long-term use, all with the intent of having less impact on the environment. I am convinced that the use of properly designed and formulated polymers can be effective deterrents to corrosion. LeVar, let us not forget that the answers we seek are all in the chemistry. And in our fight to conquer corrosion, the answers are all in the polymer chemistry.
Now let's break things down to the atomic level for a moment. Our world is made up of elements displayed on a periodic table. All life is made up of and needs carbon, and so does corrosion control. Polymers rely on a backbone of carbon and hydrogen atoms. Carbon and hydrogen can combine into a number of molecules, where the simplest is methane, consisting of 1 carbon and 4 hydrogen. And as you add more carbon and hydrogen elements, different molecules are made. Ethane has 2 carbon and 6 hydrogen. Propane has 3 carbon and 8 hydrogen. And if you add 1 more carbon and 2 more hydrogen, well, there you have butane. And larger hydrocarbon molecules such as octane carry 8 carbon and 18 hydrogen. All are created from the carbon and hydrogen elements. Now, when elements join together to make molecules, these molecules string together to form larger molecules. When joined and repeated, these molecules, or monomers, become a polymer. The simplest example of a hydrocarbon monomer is ethylene, and this element can react with itself to form a polymer called polyethylene. So, what would go into building a complex polymer? Just adding additional elements does the trick. Hydrogen, carbon, and chlorine can combine to form polyvinyl chloride, or PVC. And where is PVC commonly found? Under the kitchen or the bathroom sink in our homes, in water hoses, water beds, and even that inflatable bounce house popular at children's parties. In polyamides, we would use the nitrogen and oxygen elements to combine with carbon and hydrogen to create such common items as nylons or coatings for cooking utensils. The elements on the periodic table can be combined in a near infinite number of ways to form different polymers used in various daily coating applications. There are also protective polymers, which are used to keep people safe from things like hazardous chemicals, extreme temperatures, and fire. These polymers are often utilized in firefighter, police, and military uniforms for protection from heat, fire, biological, or chemical agents. Even spacesuits utilize polymers, offering the wearer protection from the cold vacuum of space. Now, when amide monomers are joined by peptide bonds, they become polyamides. Polyethylene consists of long chains of monomer ethylene, and PVC, or polyvinyl chloride, is the polymerization of the monomer vinyl chloride. All three of these are classes of polymers that can be characterized as thermoplastics. But what is a thermoplastic polymer? Thermoplastic polymers are composed of long parallel strands of molecules which enable them to slip easily over each other. Therefore, thermoplastic polymers can be easily bent, stretched, melted, remolded, and recycled. The second category of polymers used for protective coatings are known as thermosets. Now, this is when polymers have covalent bonds along and between the strands of molecules. We call them crosslinks. These bonds limit polymer chain mobility, and as a result, the polymer chains break and decompose when heated rather than melt. The difference in using thermosets versus thermoplastics is that the cross-linking of thermosets imparts more barrier properties. Some barrier properties include chemical resistance, water resistance, and resistance to the oxygen and ions that fuel the electrochemical corrosion process. While we are taking a closer look at thermosets, let's go into the different classes of thermoset polymers that can be found. The ones that are useful as protective coatings are epoxides, alkyds, polyureas, phenolics, polyurethane, acrylic, and polyesters. Epoxides are cyclic ethers with 3 ring atoms. Now, the ring found on these atoms defines an equilateral triangle, thereby making the ring highly strained. The most common use of this thermoset is that it's used as primers for metals and as multi-layer protection on pipes. And the downside is by using an epoxide, sunlight can affect the chemical and peel it away in sheets. Alkyds have a polyester backbone with a fatty acid side group. Their primary use is as an appliance coating, and they are usually less expensive than epoxides. Polyureas are similar to a polyamide in that there is a nitrogen molecule on either side of the carbonyl group. The primary use for polyureas is as a coating for pipes, much like the epoxides that we discussed earlier, but they are sometimes used in place of epoxides as they are not affected by sunlight. Phenols or phenolics consist of a hydroxyl group bonded directly to an aromatic hydrocarbon group. These are most widely used inside of cans and are FDA approved. The mixture of chemicals and foods can strip the tin coatings in a can, so phenolic coatings are used to keep the inside from corroding due to these food chemicals. Now, let's check in with Professor Mark Socek from the University of Akron.
In a typical coating system, there are multiple coating layers each to protect each other. For example, in an automobile, there's cleaning, a pre-treatment, which is mostly inorganic, and the pre-treatment is meant to protect the metal substrate against corrosion. A primer goes on top of that after the pre-treatment is dried and cured, and the primer is meant to protect the pre-treatment. A top coat goes on top of that, and the top coat is meant to protect the primer. So, in other words, it's three separate coating steps, all working as a system. Smart coatings need smart processing. For example, this state-of-the-art, one-of-a-kind processing machine has 4 curing chambers, 2 UV, 2 thermal, with feedback loops using IR and Raman spectroscopy. It also has this state-of-the-art nanofiber spinning that's good for electromagnetic shielding and anti-static coatings.
Now, so far, we have dealt with some pretty serious chemistry technobabble. So now let's take a step back to look at the history of polymers and learn where their use as corrosion protection began. Since the beginning of life on Earth, mankind has been utilizing organic polymers from the animal kingdom, insect, and plant worlds in order to help protect and preserve metals. An early version of thermoset polymers were lipids, which are oils and fats made from triglycerides. These form the oldest known protective coatings. Fat would become oil when heated and applied to metal, then heated again to provide a water-resistant coating. Iron, for example, had many issues with corrosion, but by utilizing lipids, these issues quickly became less of a problem. Fish oils, another lipid, were found to be a fantastic protective coating after Robert Ferguson mistakenly spilled a barrel of fish oil on the deck of his ship. The corrosion occurring in the area of the spill magically slowed. The observations he made after this fish oil incident led him to the creation of the world's first rust-preventative paint. Complex phenol molecules that make up old tree sap were also used as early thermoset polymers. These tree resins were used in conjunction with lipids to form harder, more durable coatings, and not only used with metals, but with woods as well. The last two old-school protective coatings are derived from insects. Chitin is found on the exoskeletons of many crustaceans like crabs, lobsters, and shrimp, and on insects including ants, beetles, and butterflies. It's often used as a binder in dyes, for water purification, or as an additive to thicken and stabilize food and pharmaceuticals. Shellac would be an early version of a thermoplastic polymer which is still currently used, and it will be the final coating we will look at within the history of polymeric coatings. Shellac is a resin secreted by the female lac bug, which forms a cocoon in the trees in the forests of India and Thailand. Shellac is dissolved in denatured alcohol to make a liquid used as a brush-on colorant, food glaze, and wood finish. So, the next time you're about to pop a color-coded chocolate candy in your mouth, look closely for a moment as you're actually eating a bug secretion that is commonly used as a protective coating. That's good bug secretions. Shellac has the record for the longest commercially sold coating formulation in modern times. That's 100 years and still counting. Okay, so how about the way coatings are applied? And how has this changed over the years? Well, the oldest method of applying a coating onto a surface is called wiping. Plant or animal materials such as chamois cloth, cotton cloth, and wool were always used. For fine cosmetic wood finishes, these methods are still used. Brushes, which were composed of animal hairs and bristles, were later replaced by nylon brushes. However, these two methods were deficient for corrosion protection, and the old way of wiping a coating onto the metal became outdated when brushing became the norm. After brushing, rolling took over and carried on until the age of dipping. Today, we live in the age of electrodeposition. Electrodeposition utilizes electrochemistry to apply paint to a metal. You can e-coat, another term for electrodeposition, either anodically or cathodically. Anodically, a negatively charged paint colloid is attracted and migrates to the positively charged metal cathode. Cathodically, a positively charged paint colloid is attracted and migrates to the negatively charged metal anode. The material that needs to be protected is submerged into a water-based coating. In this water-based coating, the polymer, pigment, and additives are dispersed but stable until it is attracted to the metal electrode. An electrical chemical reaction occurs to neutralize the coating, depositing it evenly on the metal substrate. As we all know, corrosion begins with a defect, either in the coating or the substrate, but by being able to control film thickness, the polymer deposits on the metal until nearly defect-free. This groundbreaking technology has been in use since the mid-1960s, when it was first adopted by the American automotive industry for use on the vehicle assembly line. Within 2 years, it became the standard technique for corrosion protection in the automotive industry worldwide. Continuing with our discussion about coating application techniques, using coulombic forces in which opposite charges attract brings us to electrospraying. Both solids and liquids can be electrosprayed. With liquids, the metal is charged and the spray gun is oppositely charged. As the liquid is atomized, it is charged and attracted to the oppositely charged substrate. The process of electrospray is useful in that it is highly efficient, more so than normal spray techniques because of the attractive forces involved. Powder coatings are also electrostatically sprayed, but they are applied directly to the metal. Again, the powder and the metal are oppositely charged and attracted to the metal substrate through static attraction. The powder, once deposited, is placed into an oven and heated until the powder becomes a liquid, forming a continuous film. Some advantages to powder coatings are low VOCs, low toxicity, and explosion hazards for ovens, lower handling costs, and a 95% utilization of resin. On the negative side, there are issues with pigment and appearance. It's not recommended if you are working with heat-sensitive substrates, and there can be issues with particle size, thickness, and multiple passes. In addition to the polymeric matrix, pigments and additives also contribute to corrosion prevention. Particles typically come in various shapes, such as oblong, round, or plate-like. The small molecules that contribute to corrosion, such as water or oxygen ions, only diffuse through the organic polymeric matrix and not through the solid particles within the coating. So logically, the more particles you put into your coating formulation, the more diffusion is inhibited. The shape of the particles also has a direct effect. Platelets lengthen the pathway that the small molecules must travel to meet the metal or substrate. The longer the pathway the ions are forced to travel, the more protection is afforded to the coated material. This concept is known as, are you ready? The tortuous pathway. Pigments also inhibit corrosion in a more direct way. A first example of this is zinc-rich silicate. Metallic zinc is dispersed in a silicate resin and used as a sacrificial electrode. The iron oxide and zinc metal undergo a redox reaction in which the iron oxide returns to its metallic state and the zinc is oxidized to zinc oxide. In this way, the metal surface is protected against corrosion and is more electrically positive. Another example of pigment directly inhibiting corrosion is strontium chromate. As water diffuses through the polymeric binder, the strontium chromate pigment ionizes, dissolves into the water, and is pulled into the corrosion blister. At this time, it passivates the metal, interrupting the electrochemical corrosion cell, thus inhibiting corrosion once it has already begun. Strontium chromate is unfortunately water-soluble and carcinogenic. Therefore, it is not always practical for use. As a consequence, during the course of the last 15 years, there has been a profound push to find corrosion-resistant systems to replace these chromates. There are 4 leading candidates vying to take the place of strontium chromates. The first of these is a magnesium-rich primer. A second is cerium-based, a third is based on inorganic-organic hybrids, and the fourth is molybdenum phosphate. Magnesium-rich primers are similar to zinc-rich primers in that magnesium particles have been used, but instead of using a silicate polymer binder, the magnesium particles have been used with organic polymers. However, the mechanism of protection is the same as zinc in that they are both sacrificial electrodes. The cerium candidates are similar in function to a chromate system. Cerium is water-soluble and transports to the site of corrosion where it passivates corrosion formation. A number of ways to introduce cerium have been used and tested, such as using particles of cerium nitrate or sequestering the cerium ion in a silicate such as talc or chitosan. The release of the cerium ion from chitosan is pH controlled, and as corrosion takes place, the pH changes and the release of cerium is initiated in the water, transporting it to the site and inhibiting corrosion. Inorganic and organic hybrids have to do with sol gel chemistry similar to the silicate matrix. In this case, the continuous matrix is an organic polymer such as epoxide or polyurea. Using this approach, Wright-Patterson Air Force Base developed SNAP technology which is an acronym for self-assembled nanophase particles. SNAP is an environmentally benign alternative for aircraft corrosion protection. With this technology, functionalized silica nanoparticles are formed in an aqueous sol-gel process. So the process links silicates together using epoxide and amine chemistry. In either approach, small pre-ceramic molecules react at the metal surface, passivating it and protecting the surface against corrosion. Finally, we come to molybdenum phosphate. This seems to work in a manner similar to strontium chromate, which means they are water soluble, but not carcinogenic, and thus not dangerous to the environment. Although nothing can fully stop corrosion, polymeric coatings do a good job of slowing it down. Without a coating, steel flash rusts in minutes. However, a smart coating system that has an integrated passivating agent will allow a steel structure to last more than 20 years without rusting. In the future, some metal structures will be replaced with polymeric composites. The difference between coatings and weight-bearing polymeric composites is the use of fibers to reinforce the organic polymers. Such composites are presently used in a vast array of sporting goods, replacing metal or wood in items like golf clubs, tennis rackets, skis, etc. Composites are also presently used on airplanes to replace aluminum. The Boeing 757 commercial aircraft, the United States Air Force F-22 Raptor, and the B-2 bomber are a few examples of this practice. Also, the development of thermoplastics as a load-bearing structural material has been demonstrated. Short-span thermoplastic bridges formed entirely from recycled materials, including plastic milk jugs, plastic soda pop bottles, and recycled car bumper scrap, have been molded to the point that they can hold a 71-ton Abrams tank. Amazingly, it is expected that the life of this type of bridge will be in excess of 50 years with little or no maintenance. For now, my friends, this completes our journey. But we continue to make great strides in the war on corrosion. Today, we took a look at just one of the many weapons in our arsenal, the utilization of polymeric coatings. Thankfully, their application seems to be limited only to the current technology. This means that with our limitless imaginations, we will continue to generate even greater scientific knowledge, infusing our soldiers on the front lines with superior weapons to give them a stronger advantage in order to defeat this clear and present danger that we call corrosion. Thank you for joining me. I'm LeVar Burton, reminding you once again that rust never sleeps.